Hello everyone. In this video we will be talking about Retrieval Augmented Generation or RAG. This video is not a paper review for the RAG paper, but we'll be looking into RAG from an OpenQA perspective because in this video series we're talking about how to do OpenQA using dense retrievers. So RAG first appeared in this paper called Retrieval Augmented Generation for Knowledge Intensive NLP Tasks. And Yeah, so if you remember, just a quick overview on the OpenQA setup. In an OpenQA setting, given a question or an input sequence given or X, our retrieval model returns a set of retrieved documents which we call Z, and we have to predict a final answer which we call Y. So in our last video where we were discussing about ORQA, the QA model used in ORQA an um, was an extractive model, which meant it gave the answers as the span which contains the start token number and the end token number, which tell us about the answer span of the answer in our context. RAG was one of the first papers in which the QA model used um, for the answer generation was a generative model, which basically meant that each and every token was generated at a single time, and if we don't give answers in the form of spans. So before we go ahead, we should formally write the two most important components that we'll be working with. So first one is the probability of documents which we get from retriever. Here in the paper it is denoted as probability of n, where n denotes the retriever here of a retrieved document given an input question like X. And similarly, the generator here in since it's a generative QA model, we directly call it as a generator. Here, which is called as the theta part of the model. So p theta of yi of a one particular token will depend upon the input context or the input question and the retrieved document and the tokens that have come before it, so from I to I minus 1. Yeah, so this is the probability given from our QA model, and this is the probability that is given from our retrieval model. So before we go further, let's talk a little bit about how a generator model usually gives probability to a target sequence. So mostly in generative models, as we discussed in our first video, the probability of a target sequence is given an input sequence is the multiplication of probability of each and every token that came here. So using the above notation, it will be the probability given by the QA model of yi token given the input X and all the tokens that came before it, I to I minus 1. Here we are not, let's not use theta here because we are just in general talking about the probabilities of a sequence of the output sequence in a generative context, and we multiply them over all the token values. So if I try to explain this simply, let's say our target sequence is I am Akash. So the probability of getting this target answer, this target output sequence, is the probability of getting the token I times the probability of getting the token M times the probability of getting the token Akash. Now each of these tokens, they depend on what all tokens came before them, and this is in a generative sequence to sequence model. We generally do it using masks, in which at decoder time the current input sequence cannot, let's say for this token number 2, it won't be able to see any values for tokens which is greater than 2. For all the tokens that are greater than 2, it can only see the information from its past. So how do we represent the final probability of the output sequence? Probability of I am Akash is the probability of this expression here. So mathematically we represent this as the multiplication of probability of each of the individual tokens, and that is this here. So probability of the present token given the input question and all the tokens that came before it. So this is the probability of a target sequence in a generative setup. Now our RAG formulation, in RAG paper there are two main formulations, which is the two main parts of this video also, which is the RAG sequence model and RAG token model. So let's see what that means. So let's say in an OpenQA setup, again taking the same target sequence, we want the probability of getting this as the target sequence. So there are two ways. Since in OpenQA there are intermediate variable, which is the retrieve document, they are present. There are two ways how we can get this final output sequence. So let's say for our case we are taking the case of 5 retrieve documents. So let's say 1 2 3 4 5, and again for the same scenario, for a different scenario, 5 different documents. So there are two ways in which we can achieve that. Either we see from each retrieved document what is the chance of getting this particular sequence as an output. Let's say I am giving some context, and when I pass this context to a QA model, what are the chance of getting this as the output sequence? What is the chance of this output sequence? And similarly from this, this is Z1, this is Z2, let's say this is ZK. Okay, Z5, let's take Z5. So what is the probability of getting I am Akash from Z2? So this is one way in which for our target sequence we try to derive its probability from by giving the QA model each and every block as a separate input. Now another way of approaching this is, let's say I want the same target sequence. So let's say if I want the probability of this this target string, the another way that we can use is that for each output token we take into consideration all the retrieved documents at the same time. So here we're considering while predicting the final output, we're considering only one retrieved block at a time, and here we consider all the retrieved block at the time, and all the retrieved blocks at the same time, and that somehow enables us to get different kinds of information from different retrieved blocks. So formally they have mentioned these approaches as the RAG sequence model. This one is RAG sequence model, and this is the RAG token model. So we'll look into both of these approaches in much detail now. Okay, so let's continue on RAG sequence model. So now as we discussed earlier, the probability of we want to see how can we get the same how can we get the target sequence from each of these retrieved documents. So let's say if I finally want to get the probability of the answer string, I am Akash, given an input X. So in an sequence model settings, it will depend on, we can get this 5 different ways, right? So first one is when we get this, let's say this is equal to capital Y. So this answer string I am Akash is the capital Y. So first one is that we get capital Y from the input sequence and the first document. So this value will inherently depend on the probability of getting the first document PZ1 given X. Why? Because if we remember in previous videos we have discussed about this, that let's say if we are asking a specific question related to rocks, and if we get the Wikipedia article of getting of rocks, then the answer of getting the chances of getting correct answer from that article is very high. So the probability of the retrieve block is important here. Similarly, if we continue the another way of getting the answer string I am Akash will depend from pz2 given x. Another probability will be and probability of capital Y given x comma z2, and we do this all the way to probability of z5 given x times probability of getting I am Akash from x and z5. So if we try to write this mathematically, this is nothing but the original, the QA formulation that we have been using till now, which is summation over z probability of z given x times probability of y. I'm using capital Y here, but we'll generalize it soon. Capital Y given x comma z, right? So this was probability of capital Y given z given x. So when we generalize it to any possible target sequence, what we do is we replace capital Y with small y, and z, probability of z given x, probability of small y given x comma z. And now we know that in our generative setup, what is this value? This value is probability of z given x. This value is probability, individual probability of multiplication of all the probabilities in the target sequence. So this becomes probability of yi given x comma z and all the tokens that came before it, which is from I1 to I minus 1. So in the sequence model type, in the RAG sequence model, this is the probability of a target sequence. Now how do we calculate it in code? We'll talk in such a way that when you actually see the code also, it's much easier for you to grasp. So how do we do this? So generally what we have is we'll give the model input a batch of questions, or we can take here batch size of 1 also. But when we include batch, it generalizes well to our applications. So for each batch, the model will retrieve some top K documents. We reshape them to the size of batch size into top K and pass this entire thing to our QA model. So our QA model will return logics of size, batch size into top K, comma, sequence length and vocab size. This is pretty standard stuff. This happens in all the QA models, so it shouldn't be confusing. And similarly, we'll have our targets. Our targets will be of shape, batch size into top K, comma, sequence length. Okay. So this is our initial setup, and we have passed our inputs and we finally got these logics. And now let's see how do we calculate each and every part of this expression here. So first we'll try to get the values for this part of the expression here. So this involves, since it involves a lot of multiplication, it's a good idea to do it in log space. So when we do the log of these values here, what we get is the log of p eta, oh sorry, I should write here, I removed it, p n and p theta. So p eta given z comma x plus summation of I over n log of p theta of yi, yi given x, z and y, all the previous token yi to I minus 1. Okay, so how do we get these values? So in our code and in generally we get these values in which this is something called as doc probs, and they are of this shape, batch size comma top K, which basically tells for each of the question what are the top K probabilities for each of these retrieved documents. So for our case here, we reshape it to batch size top k, comma 1 comma 1. All right. And here, as we remember, our logits are of this shape, right? So what we do is we reshape them into in this way, so they become batch size, top k, sequence length, and vocab size. Since we have to add these values, we kind of add these values here. We do an addition of them, and in code they've done it in a different way, but we can still continue in this formulation. So finally we get a tensor of shape, batch size, top k, sequence length, and vocab size. So what we have essentially done here by adding these is that we have multiplied the probabilities of the retrieved probability of the retrieved document times the probability of each and every token that is possible here. So let's say in our vocab size, for each of the sequence length position, let's say sequence length position 1 and 2, we'll have the entire vocab here, right? So all the tokens that can be part of our answer, and that can be any tokens depending on your tokenizer. Let's say, again using the same answer, I am Akash. So for each of these tokens probability, they let's say their original were 0.01, 0.01 and 0.01. What we have done is we have added these values, the doc probs here for each of the retrieved documents. So let's say for the document number 1, the probability of probability of that retrieved document was 0.02. So what essentially we have done is we have done 0.1 plus 0.02, 0.1 plus 0.02, and added this 0.02 value to all the tokens that are present in the vocab. So which is something similar to doing probability of x into probability of y, but since we are doing it in a log space, this turns into addition. So now that our vocab size involves so all the tokens in our vocab size, their probability, and oh sorry, I forgot to mention that we take a log softmax of these values here, so that we get the log values. Here we didn't get the log values, so we take a log softmax of these values in the dimension -1, so that we get the log values, log probabilities. Okay. So yeah, so all the tokens in the vocab size now have the corresponding probability from which these answers were taken from, included in their probability score, log probability scores. So again we are left with with a tensor of size, batch size, top k, sequence length, and vocab size. Now here we want to find the probability of a target sequence, which here in our case was I am Akash. So what that means is that for the in sequence length for the position 0, we'll get the probability of ith token from vocab, and for the sequence position 2, we'll get the probability of the token am in this entire vocab. And when we do gather for all of these values, we get a tensor of shape, batch size, comma top k, comma sequence length, comma 1. Now since sequence length need not be necessary to the actual target answer, so generally what we do is we'll have separate token, and then most of it will be followed by padding depending on the sequence length that was chosen for the batch. So what we do is we mask all the values which contain the pad values, and then we remove this dimension to finally get a tensor of shape, batch size, top k, and sequence length. So as you see, we are still trying to find the value of this expression here, the log of this expression, And there is still one part that we have still not focused on, which is the summation for all of the sequence length token. So when we do that, we take summation of all the sequence length token, will be uh, given a tensor of size batch size comma top k. Okay. um, so this value, as discussed, represents the function value for till here. We still have to do a marginalization over the retrieved documents. So as you remember, our cost function in OpenQA setting, for especially for RAG sequence model, is marginal log likelihood. So which is nothing but the negative log of marginal probes. And how do we get marginal probes? Here we'll have to sum over all the retrieved documents. So to implement this, we implement the log sum exponential function, which will do the same thing that we want. Why exponential? Because we have done this the calculation for this entire expression here, from here till here, in log space. So to keep the numerical value same, we have to take an exponent of the same function. And then when we do the sum, we do in the dimension of top k. So when we do all this operation, what we get is a tensor of shape batch size, which is the loss value for our RAG sequence model here. And if we want, we can further sum it to get a one single loss value. There's one more thing that I have to add here, which is that in paper they have added in the code they have added an smooth objective, which we have not talked about here. But I hope it is clear, RAG sequence model and how it is implemented. Yeah, so let's now talk about RAG token model. So in RAG token model, as we discussed earlier, we try to get only one output sequence, and we try to take information from each retrieved block, so that we can get different context from each document. Let's say we are trying to predict the same answer string. I am Akash. Now, as we discussed in the beginning of this video, the probability of getting this sequence will be, let's say this is equal to capital Y. Capital Y given X will be the probability of getting the token I, probability of getting the token I, and probability of getting the token M, multiplied by probability of getting the token Akash, which we finally wrote as the multiplication of all the tokens that are present and probability of each and every single token given X and all the previous tokens that it has seen till now. Now in our RAG token model formulation, each of these probabilities can come from different we have to find the probability of getting I from each and every of these documents. So if we try to write it correctly, this becomes for in an RAG token formulation, probability of an output sequence given X is equal to the probability of each and every sequence, each and every token in the sequence given the input X and all the retrieved documents and all the tokens it has seen till now. Okay, now but what is the value here, right? So previously in RAG sequence model, we were trying to get the probability of the entire answer sequence from each individual block times, then it was probability of the second block times the probability of getting the output sequence, getting the output sequence here, all the way till P for the final retrieved document, probability of I. But here in our case we'll be doing the same thing, but we'll be doing for each and individual token separately. So for the probability of getting I, which is our let's say I equal to 0, 0th token, it will depend on probability of getting the first paragraph, first retrieve block times the probability of getting I token from there, and similarly adding probability of getting the second block. And what is the probability of getting I as the 0th token? We have to keep that in mind, the probability of getting I in the 0th token. And similarly we added for all the values for all the retrieve blocks. So probability of getting I from the 5th retrieve document. So as you can see, what is happening here is that this expression here is equal to summation over all the retrieve blocks, probability of getting that particular retrieve block times getting the probability of that particular token given the context or the input question and the retrieve block, this particular retrieve block, and all the tokens that have come before it. Understand? So this expression here is the value for this. So the ultimate value, the value for this we can rewrite as probability of RAG token give for a target sequence y given x is equal to multiplication of the individual probability of getting each token when it is taking context from each and every retrieve block, summation over all the retrieve blocks p eta of n z given x times p theta, which is given by our QA model, times that particular token given x, the context, this particular retrieve block, and all the tokens that came before it. So this is the formulation in the RAG token model. So how do we calculate it in code? So continuing from the same place, we pass a tensor of size batch size into top k, which represents the for each question the top k retrieved documents. We pass it through our QA model, which gives us the logits of shape batch size into top k, comma sequence length and vocab size. Correspondingly, our targets here are also of the same shape, which is batch size in targets, batch size into top k, comma sequence length, which we reshape to batch size into top k, comma sequence length, comma 1. So kind of a similar initial setup from our RAG sequence model. So the first step here is that we want to marginalize the probabilities for all the retrieved documents before. That was something that we did last in RAG sequence model, but here we'll be doing first because probability of each single token will differ when it's taking context from different documents. So from a QA model, we got a tensor of we got the logits of shape top k, comma sequence length and vocab size. We reshape this tensor to a shape of batch size, comma top k, sequence length and vocab size. So first what we'll try to do, we'll try to get this value here, this value, and we'll similarly if in the last the way we did it last time, we'll try to do it in log space. So when we try to do it in log space, what we get is log of p eta given z comma x plus log of p theta yi yi and x z and all the previous tokens. All right, so this is something that we get from a retriever, and it is of the shape batch size comma top k, but we reshape it to batch size comma top k comma 1, and this is already of the shape here, this shape, and what we do is we add both of them and we get a tensor of shape batch size comma top k comma sequence length comma vocab size. One more important thing is that we have taken a log softmax. I keep forgetting mentioning about log softmax. So these were the logics for the retriever. These were the retrieval probabilities which we got after taking log softmax of the docs course. And similarly, we take a log softmax in the dimension equal to -1 for this expression also, which gives us the log probabilities. This tensor here represents the probability of each and every token in the vocab for the each and every possible position in the target sequence for each of the possible when we are taking inference from different top-k documents. But in our formulation, we have to adjust the probabilities of these two so that they take into account of taking probability and taking information from all of these retrieved documents. So to do that, we have to marginalize over these documents, over these top-k documents. And when we do so, we do a log sum exponential function here. So till now in this expression, what we have done is we have calculated the value for this thing in the log space. Okay, so what we do is since it is in log space, to keep it numerically same, we take an exponential, then we take a sum in dimension equal to 1, and we take the log of this entire thing here from here till here. So when we do that, we get a tensor of shape batch size comma sequence length from vocab size. So what we have done here is that for all the possible sequences, and let's say if we were considering I am Akash only, right? So for the sequence length position of 0, that is when we are for the target sequence, we're thinking about this particular token, we have adjusted the probabilities, log probabilities, in such a case that it is now considering getting the probability of I from each and every individual retrieved document. So now finally, from our target variables, from our targets, we do our gather for our target sequence, so which would give us something like a tensor of shape batch size comma sequence length comma 1, which this tensor here might also contain the pad values also, pad tokens also, so we mask them and we reshape this, which gives us a tensor of shape batch size comma sequence length. Okay, now a cost function here, if you remember, was in a generative QA model, it is the negative log likelihood, right? So what happens is that from p of I of x, it is multiplication of I over n probability of yi dot 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 whatever happens here, and we take negative log likelihood, which turns this into summation of I over n log of p of y of I given all the values, intermediate values on which we depend. So if you notice, this value here is already the log value, of this thing entirely here. And to finally get our expression, all we have to do is do a summation in the sequence length, in the token in the sequence length dimension of our tensor, which in the end returns us a tensor of size batch size, which gives us the loss value, and if we want one concrete loss value, we take a sum over all these batch size values. And again, in this part also, in RAG token model, they have added a smooth objective which we have not discussed it. So that's it from my side. I hope I made it clear and it was helpful for you guys. So see you in next video. Thank you.